Hi, welcome to Chemical Bonding Review Part 4. Today we're going to be looking at the concept of metallic bonding and other important things to know about chemical bonding. Today we're going to look at what is a metallic bond, what is a network solid, what's a coordinate covalent bond, what is a polyatomic ion and how we relate coordinate covalent bonds to some of them, and compounds that have both ionic and covalent bonds. So let's talk about metallic bonds first. Metallic bonds are basically the bonds that are found in metal. When we talk about metals, we know that they have low ionization energies and they tend to lose valence electrons. So the electrons are basically mobile. So let's think about metal in general. We know metal is made up of metal atoms. They have these low ionization energies. The electrons are able to be mobile. So how do we relate a metallic bond? The easiest way to visualize this is in terms of the electron sea model, or sea of electrons, where all atoms lose their valence electrons. And as you can see from this diagram right down here, we have a positive nucleus and the idea that these electrons are going to be moving throughout this entire metal substance. So in other words, the valence electrons are no longer localized on a single atom, but are delocalized or away from their particular atom and moving among other positive nuclei over the entire metal. So when we talk about metallic bonds, think of the idea that these electrons, these valence electrons, are able to move. And because they're able to move, that's the bonds that are going to form between these positive ions. Now let's talk about network solids. And network solids are a specific type of compound that has covalent bonds. So this is a covalently bonded atom that extends throughout a macromolecule. They have extremely high melting points and a very strong bonding structure. And some classic examples of network solids are diamonds, as we see in this little picture down here, silicon carbide, quartz, which you might have studied about in earth science, otherwise known as silicon dioxide, which has the formula SiO2, and graphite. So if you're writing with a pencil, you're writing with graphite, and that is a type of network solid. Then we have something known as a coordinate covalent bond. A coordinate covalent bond is a covalent bond in which both shared electrons are donated by the same atom. So we can think of, when they say both shared electrons, specifically we're going to be talking about lone pairs of electrons here. Lone pairs of electrons. We see them commonly in polyatomic ions. Not all polyatomic ions have coordinate covalent bonds, but a good majority that we use in class do. And we associate the coordinate covalent bond commonly with the hydronium ion, and you'll recognize the hydronium ion off of table E, which of course is your reference table that refers to polyatomic ions, and there's two positive polyatomic ions listed on table E that we use a lot. One is hydronium and the other one is ammonium, which we'll see a little bit later. So we know that hydronium is commonly associated with acids. It's the more stable version of just a hydrogen ion by itself. So the question is, well, where's the coordinate covalent bond in a hydronium ion? Well, a hydronium ion is composed of a hydrogen ion, and we know that hydrogen ions are going to have one proton and 0 electrons. So 1 proton, 0 electrons. We know it has 1 proton because hydrogen's atomic number is 1. We know it has a positive charge because if there's only 1 proton, there can't be any electrons. The hydronium ion is going to basically hook up with a water molecule. Now, in the previous video, we talked about water and that it has a formula of 1 oxygen and 2 hydrogens. Each of these lines represent shared pairs. And then we have 2 lone pairs up here. So what's happening here? Well, this water molecule right here is neutral. It's stable. Oxygen has its full octet. Each hydrogen has its 2 valence electrons. Great, not a problem. This hydrogen ion, though, has no electrons. And we know, based on previous studies, that hydrogen, to be stable, would really like 2 electrons. So what happens here basically is that this hydrogen ion is going to snuggle up next to this lone pair right here, and you can choose either one, to form what's known as a coordinate covalent bond. So what is this going to look like? Well, we'll have our water molecule, which is right here, and I'm going to throw on my 2 lone pairs, and then basically this hydrogen ion says, hey, you've got 2 lone pairs that you can share with me. So I'm going to come right over here. but it's bringing that +1 charge with it. So that means for the hydronium ion, the whole thing has to be in brackets with a +1 charge. So where is the coordinate covalent bond? Here's the coordinate covalent bond. Okay, coordinate covalent bond, CCB. Because the oxygen itself is donating both electrons, the hydrogen is accepting them, so we find that coordinate covalent bond here, but the rest of these bonds are just typical covalent bonds, polar covalent bonds. So let's talk about what a polyatomic is. And if we look at the word polyatomic, we know that poly means many, and atomic means atom, and then an ion, which means that it's going to have an overall charge. So when we look at the definition of a polyatomic ion, this is a charged chemical ion that is composed of 2 or more atoms covalently bonded together. And it just may contain 1 or more coordinate covalent bonds. May, not all the time, but sometimes it does. So we're going to look at the nitrate ion. Now, what's the probability of you being asked on the Regents exam to draw out the Lewis dot diagram of something like a nitrate ion? It's not going to happen, but understanding how these nitrate ions come together, how they are covalently bonded, and remember, I'm just showing you one way of doing this. If you go on and take AP chemistry, you'll be introduced into a concept called resonance structures, or maybe if you're taking honors chemistry, you've already seen this, but in a very general sense, this is just showing you where the covalent bonds are in this nitrate ion and where we might see a coordinate covalent bond. So if I look on table E, I know that the nitrate ion is NO3 - 1. Now if I was to do the Lewis dot diagram of this, I would say, well, let's start with the nitrogen, and it has 5 valence electrons. 1, 2, 3, 4, 5. And then I have 3 oxygens, so just for giggles, even though I ultimately know this is not going to work, I'm going to put an oxygen here, here, and here, and I know that each oxygen has 6 valence electrons. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and then finally 1, 2, 3, 4, 5, 6. Now here's the issue. Here's a covalent bond, here's a covalent bond, here's a covalent bond. I have my lone pair up here, but the overall charge on this nitrate is -1. And technically, I have 3 spots, 3 electrons that really need to come in to satisfy the octet rule for each one of these atoms here. So technically, if I was going to do this, I'd need an electron here, because that makes 8 in there. I would need an electron here, and I'd need an electron here. But that's not the case. Nitrate doesn't have a -3 charge, it only has a -1 charge. So is this going to work? No, it is not going to work. So we've got to take a different approach to this, which pretty much means let's bring in a coordinate covalent bond, and also let's put a double bond between one of the oxygens and the nitrogen. And you might be saying to yourself, God, Dr. English, this sounds really hard right now. Well, it is, but again, will you be expected to do this on the Regents exam? No, but is it good to know the background behind all this? Yes, yes it is. So let's do a nitrogen, 1, 2, make that dot a little bit better, 1, 2, 3, 4, 5. I am going to put an oxygen up here and use this as a coordinate covalent bond. So 1, 2, 3, 4, 5, 6. I'm going to put another oxygen over here to make just a regular covalent bond. So 1, 2, 3, 4, 5, 6. And then I'm going to put a double bond. So I'm going to arrange this oxygen so it's over off to the side. And I'm going to say this is going to be a covalent bond. So 1 and then another one, 2, 3, 4, 5, 6. So far I've done the 5 valence electrons with the nitrogen, the 6 valence electrons with each of the oxygens, so I'm not violating the octet rule at all. So now I want to do is just basically take into account what I have so far. So I have a covalent bond here, I have a coordinate covalent bond right here, but this oxygen has its octet, is a filled octet. The nitrogen itself with the double bond between this oxygen right here, the nitrogen has a full octet, and this oxygen has a full octet. So what's remaining? Well, this oxygen over here needs one more valence electron. So if we pull a valence electron from some outside source, maybe a group 1 metal that's giving up its valence electron, and we put it right here, now it's gained an electron. There's more electrons than protons throughout this entire compound, and now we have an overall charge of -1. So again, it's a little bit more complicated, but we do see the presence of the coordinate covalent bond. We do have a double bond here, that's fine, and we see where this extra electron would come in and why this is an ion basically with an overall charge of -1, but it still has covalent bonds. We can see these shared pairs of electrons right here saying to us, hey, yeah, this is a covalent bond, which is why you can look at some formulas and say to yourself, oh yes, this compound is going to have both ionic and covalent bonds, which we'll get to in a little bit. Let's look at some more polyatomic ion examples. And the first one I want to look at is the hydroxide ion. And this one is not going to have a coordinate covalent bond, and that's absolutely fine. So the hydroxide ion is very simply OH minus 1. Okay, OH minus 1. So if I take an oxygen and I put its valence electrons around it, 1, 2, 3, 4, 5, 6, and then I say, all right, let's bring in a hydrogen. So I'm going to put hydrogen with its one valence electron right there, and then I can say, well, here's my covalent bond right here, but the overall charge is -1, which means another electron needs to come in, let's say right here. So once we've gained that electron from somewhere else, typically a metal, once we've gained that electron, now the overall charge on this polyatomic ion is going to be -1. Let's look at the sulfate ion. Now the sulfate ion, according to table E, is SO4 -2. Now this one's pretty intense. We've got a sulfur atom in the center as our central atom, and then we've got 4 oxygens going around the outside. So I'm going to say sulfur and its 6 valence electrons, 1, 2, 3, 4, 5, 6. I am going to put an oxygen up here, and one here, and one here, and well, that's a sad looking oxygen. Let's do that. And then one more over here. So these 2 oxygens right here are going to have coordinate covalent bonds. So if I put electrons around them, 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6. And then I'm going to look at these 2 oxygens over here, which is just going to have a regular covalent bond, a shared pair of electrons between the sulfur and the oxygen atoms. So I'm going to say 1, 2, 3, 4, 5, 6, and then over here, 1, 2, 3, 4, 5, 6. So the sulfur has its 6 valence electrons, and each oxygen has their 6 valence electrons. And again, I can look at these oxygens and I can say, well, this is a coordinate covalent bond, this is a coordinate covalent bond. So let's make a note of that, coordinate covalent bond, because these oxygens are accepting both of the lone pairs from the sulfur atom right here. But again, we see the situation here where these oxygens do not have their full octet. So if we bring in 2 electrons from an outside source, maybe two metals from group 1 or a group 2 metal, which are going to donate their electrons, we'll put one of the electrons right here, and we'll put one of the electrons right here. And again, now we're going to have more electrons than protons. So the overall charge on this is going to be -2. So again, what's the purpose of doing this? The purpose of this whole exercise is to, 1, recognize the fact that these particular ions do have coordinate covalent bonds, and 2, to see the covalent bonds that actually exist within these polyatomic ions. Now let's look at a situation where a compound has both ionic and covalent bonds and how to recognize them. So if I look at sodium hydroxide, that's going to say, well, I have sodium, which is Na, and it has 1 valence electron, and hydroxide. I look at table E, and that is OH minus 1, so OH minus 1. So how is this going to work together? Well, let's take sodium. Sodium is going to give up its 1 valence electron. That's what it's going to do. So if we start out by drawing the polyatomic for the hydroxide, we'd say oxygen, 1, 2, 3, 4, 5, 6. We're going to bring a hydrogen here. So let's put for giggles, let's put the hydrogen on the bottom. There we have our covalent bond right here. And then the sodium is going to basically donate this electron right here to this spot over here. So if the sodium donates its electron, we're going to have Na plus 1. That electron is going to go right here to help oxygen fill its octet, and then the overall charge here is going to be minus 1. So this bond right here is a covalent bond. Covalent bond. Okay, covalent. We're sharing electrons. But the interaction between the sodium ion right here and the hydroxide ion right here, this positive, negative force of attraction that's holding this particular compound together, this is ionic. This is an ionic bond because of this positive, negative force of attraction. So sodium hydroxide, NaOH, has both ionic and covalent bonds involved in it. And in a very simple sketch right here, if we go to ammonium, and ammonium was the other positive polyatomic that I was talking about. So if I know ammonium is NH4 plus 1 and chloride is going to be Cl minus 1. So let's look at how these come together. So I'm going to have nitrogen as my central atom. It has 5 valence electrons. 1, 2, 3, 4, 5. 4 hydrogens. So 1, 2, 3, and here's that 4th hydrogen right here, and there again is here's my coordinate covalent bond right there. So 3 regular covalent bonds, 1 coordinate covalent bond, and the overall charge on this is going to be plus 1. And then I have my chloride ion, which is Cl minus 1. So again, between the nitrogen and the hydrogens, I have covalent bonds. Covalent bonds going on here. But the interaction between the ammonium and the chloride, because ammonium is positively charged and the chloride ion is negatively charged, that is my ionic bond. So if I look at the formula for ammonium chloride, which is NH4Cl, I'm going to be able to say to myself, well, that's a polyatomic, it has covalent bonds, but the interaction between the ammonium and the chloride ions are ionic, so this has both types of bonds involved in its overall structure. So what did we learn? Well, we went over the concept of metallic bonds. We looked at the properties of network solids, and I gave you some examples. We talked about the definition and some examples of polyatomic ions, and specifically talked about how coordinate covalent bonds are also involved in these ions. And then we looked at some compounds that have both ionic and covalent bonds. Need more help? Contact me. I'm always looking for feedback. I hope this was helpful. Have a great day.